Okay, Lab 4. Lab 4 is the spectrophotometry on biomolecule assay. So what it means is you're going to use a spectrophotometer to quantify the amount of biomolecules you have in your sample. Okay, so first of all, let's talk about spectrophotometer. So it's an instrument that is used a lot in the lab, especially the biotech industry labs. Okay, so it is used for various types of quantification assays. So spectrophotometer uses light. Okay, so when light interacts with a matter, so light can either transmit through a matter, or it can be reflected, bounced off, or it can be scattered by the matter. Okay, or it can be absorbed. The energy could be transferred and it could be absorbed. So there are various types of possibilities, right? But however, that matter happens to be liquid. Okay, if the object is liquid, the light can either be absorbed or is transmitting through that liquid. So there are only two kinds of possibilities. So the spectrophotometer that you're going to use in the lab will use that principle. Okay, you will have liquid sample which will be contained in a special container called a cuvette. Okay, and then you're going to shine a light on to that sample, either visible light or UV light, and the light will either transmit through that sample or it'll be absorbed. Okay, so that this machine instrument will measure the amount of light that's transmitted. Okay, so that's what it's going to do. So the amount of light that's transmitted through your liquid sample equals the light transmitted through the sample divided by the light transmitted through the blank. What it means is you will have to have some kind of control standard that doesn't have any of your sample. So we call it a blank cuvette. So blank cuvette is normally made with the solvent that dissolves your sample, but it's the solvent only. Okay, so since the blank cuvette doesn't have any of your sample, it's going to just have the background transmittance only, right? So the only true transmittance will be your sample that's dissolved in the solvent. Okay, so percent transmittance is transmittance times 100%. Okay, so transmittance is normally between 0 to 1, so 1 being the 100% transmitted. Okay, that means there's no absorbance. So there's a relationship between absorbance and transmittance. So if you have 100% transmittance, that means there's no light that's absorbed by your sample. Okay, and if you have a high absorbance, then of course the amount of light that's transmitted through your sample will be very little, very small. Okay, and absorbance is negative log 10 of your transmittance. That's a relationship between these two values, transmittance versus absorbance. Another important thing about the spectrophotometry is this fact that the concentration of analyte in the solution and its transmittance do not have a linear relationship. They have a negative log relationship. But the absorbance and the concentration of analyte has a linear relationship. So you use the absorbance of your sample to estimate its concentration. That's the principle. Okay, and then for your spectrophotometry assay, you should have a special sample holder. Again, that's a cuvette, which is made up with the material that doesn't absorb the light by itself. Okay. Quantification of macromolecules using a spectrophotometer. So like I said, there's a linear relationship between the absorbance and the biomolecule concentration. If it's a DNA, okay, for example, if you use UV light at 290 nanometer range, yes, there's a correlation between the concentration of the DNA between 5 and 100 microgram per mil concentration and the absorbance of DNA sample. That's measured by the spectrophotometer. Okay, and the linear absorbance range, if it's a protein, you will use UV light of 800 absorbance at 280 nanometer range, and the protein sample in the concentration of 0.1 to 5 milligram will have a linear relationship with the absorbance of its sample in the spectrophotometer. Okay, and there are major reference points in your spectrophotometry based quantification. For example, if you're dealing with a DNA sample, okay, the absorbance of 1, okay, using a spec, especially if you're using 260 nanometer wavelength light, UV light, okay, then observance of 1, normally that means you have about that much of DNA sample. That much is 50 microgram per milliliter concentration sample. Okay, because many scientists have done the measurement with different types of DNA samples and they figured that relationship. Okay, so if you have that concentration of DNA, 50 microgram per mil, it turns out the observance of a DNA sample will be about 1 observance unit or optical unit. Okay, that's well-known reference point. And if you have single-strand DNA, so normally DNA is double-stranded, that's a natural form, but you can have them denatured, so their hydrogen bonds are broken. They can exist as a single-strand structure as well. If that's the case, the observance will go a little higher compared to the concentration, right? So if your DNA sample is all denatured, it's existing in single strand, then 1 observance unit equals about 33 microgram per milliliter concentration. Okay, so that's the reference point. And then if we have a pure RNA sample, it's made up with all RNA sample, okay, then 1 observance unit, OD unit, equals about 40 microgram per milliliter. Okay, these 3 reference points are really important when you try to quantify your nucleic acid sample, either DNA or RNA or single-strand DNA. Okay, you can use this reference point in your calculation. Okay, so here's an example question. If you have a DNA sample and you diluted your DNA sample to 1 to 100 ratio, and then your diluted sample showed you about 0.25 OD at 260. Okay, so it's a DNA sample again, so probably it's a double-stranded form. Okay, you have to use that reference point. Okay, so how much DNA sample concentration do you have in the undiluted condition? Okay, that's the question. So how would you figure it out? So if it's a double-strand DNA, 1 OD equals 50 microgram per milliliter, right? But now you have what? Only 0.25 OD, so it's a 1/4, a quarter of that concentration. Right? So what's the concentration? 50? So a quarter of 50 is what? 50 divided by 4, so which will be what? 12.5 or something like that, 12.5 microgram per mil. But again, you have to consider the dilution here. So the original DNA sample, which is not diluted, will be 100 times more of the concentration. So you have to multiply 100 by that. Okay, does it make sense? That's how you're going to do. And this one, if you have RNA sample, okay, so that RNA sample's dilution, 1 to 10 diluent, gave you 0.1 OD at 260 observance unit, okay, 0.1. So if it was 1, it was 33 microgram per mil, but it gave you 0.1, so it's about what? 3.3 microgram per mil, but it was diluted to 1 to 10. So actually the original sample was 10 times more diluted, 10 times more concentrated. So it should be 33 microgram per mil. That's how you can figure out the DNA and RNA concentration based on the OD, the spectrophotometry observance unit. Okay, straightforward, right? And then based on the 260 and 280 observance unit and their ratios, you can estimate the purity of your DNA or RNA sample, because the ratio of 260 over 280, okay, that varies, depends on the concentration of your DNA or RNA. Let's say you have a pure RNA, it's all RNA sample only, and if you take your RNA sample and do the 260 spec reading and 280 spec reading, and if you divide 260 reading, spec reading by 280 reading, it turns out the ratio is close to be 2 if you have a pure RNA sample, okay? But if you have a pure DNA sample, okay, and did the spec reading at 260 and 280 and figure out the ratio, the DNA sample will give you about 1.8 ratio, okay? So there's a unique characteristic between RNA and DNA, the ratio of 260 over 280, they are kind of unique. But then if we have a pure protein sample, the ratio is different again. The ratio is only 0.6, okay? So they are widely different. So what do they mean? What they mean is, let's say you have a DNA sample and you try to quantify its concentration by doing the 260 reading, yeah, you can do that using that reference point of 50 microgram per mil equals 1 OD. That's fine. Okay, you can also take 280 reading of your DNA sample and then do the ratio 260 over 280 and see what the ratio you get. If the ratio happens to be close to 1.8, that means your DNA sample is pure, it's all DNA. But if the ratio happens to be close to 2, that means you have some mixture of DNA and RNA. If that ratio happens to be close to 2, that means you have a lot of RNA in your sample. Okay, that's how you can estimate the purity of your DNA sample. Okay. So the lab exercise 1. So you will be given with the unknown DNA sample, maybe sample A and B, unknown DNA sample A and B, and unknown DNA sample and RNA sample A and B. And you will be asked to quantify them by using a spectrophotometry readings. Okay, so the amount of unknown DNA and RNA sample, they may not be a lot. They may be about like maybe 10 or 100 microliter volume. So you have to use it frugally because you don't have enough sample. You may have to dilute it, okay? Because your spectrophotometry, the sample reading takes about 1,000 microliter, 1 mil. But if you're not given it, 1 mil, you have to dilute it to make 1 mil, right? So maybe I recommend you to make 1 to 100 dilution with nanopure water, okay? And then use that 1 to 100 diluent to do the spec reading. And after calculating the concentration, you can just multiply 100 diluent to get the concentration of the original undiluted sample. Okay, so you can practice that using 260 reading. You can estimate the concentration of DNA RNA, and then I also ask you to do the 260 over 280 ratio to estimate their purity. Okay. And then lab exercise 2. So exercise 1 is pretty straightforward. It's just dealing with DNA RNA sample and doing the spec reading and get their concentration estimated and get their purity estimated. But lab exercise 2 is a little more complicated because it's dealing with the protein samples, and it deals with the Bradford protein assay. So Bradford assay is based on color. Color dye molecule that will bind your DNA. They will bind your protein sample. Okay, so the color-based assay, it'll use visible light instead of UV light. So when you deal with the protein sample assay, it's a little more complicated because